Okay, so this is our fourth problem about optimization. If you look at the problem sheet on optimization, this is actually problem number 7. Let's read the problem. A box with an open top is to be constructed from a square piece of cardboard 3 meters wide by cutting a square from each of the 4 corners and bending up the sides. We want to find the largest volume of such a box. And this is something you may have done when you were a kid, right? You have a square piece of cardboard. If you cut off a corner, a square, from each of the 4 corners, and you fold up the sides, you actually get a box with an open top. And now we're asking if you have a square piece of cardboard, 3 meters wide, and you cut off from this square piece of cardboard a square from each of the 4 corners and form a box. We're trying to find a way to cut off the corners so as to maximize the volume of our box. So let's draw a picture. We have a square piece of cardboard. And each side is of length 3 meters. So we can write here 3. So this is 3 meters. And now what are we saying? Well, we're cutting a square from each of the 4 corners. So we cut a square from this corner. We cut a square from this corner. Cut another square from the other corner. And finally, another square from the 4th and final corner. Right? So if you cut this up, so you take a pair of scissors, cut this corner out, cut this corner out, cut this corner out, and cut this corner out, you're left with the following picture. Right? This is your piece of cardboard after you've cut out the 4 corners. And each corner you cut out a square of equal size. And then you have these 4 sides, right? Imagine that you take the 4 sides and you bend them up. So if you take this side and you bend it up, take this side, bend it up, take this side bending up, and take this side and bending up, what you have is a box with an open top, right? Well, you can draw it here. It will look something like this. This is the first side by bending up this side. This is the other side after you've bent up this side. So this is your box, right? You have your square piece of cardboard. You cut from each corner a square of the same size, and then you fold up the 4 corners, and you get a box with obviously an open top. And the question is, how do you cut up the squares so that the box in the end has the largest possible volume? Well, let's see. We're asking for the length of a side of the square that we're cutting off in each of the 4 corners. That's a variable. We don't know what that is. Let's say it's x. So this is x. This is x. So if you look at the length of this here, well, this is x. This is also x. And the total length of a side is 3. If you remove x and x 2 times, you're left with 3 minus 2x. And that's the length of this side. So if you look at your cut up piece of cardboard here, the length of this is 3 minus 2x. The length of this is also 3 minus 2x, right? We have a square, so it's the same argument. This is x, so you're left with a segment of length 3 minus x, 3 minus 2x. And if you look, this is the dimension of the base of your box, right? It's a 3 minus 2x by 3 minus 2x squared. If you want the volume of this box, you have to find its height. Well, if you look, the height of the box is the length of one of the sides. And if you look, you ask, well, how long is this? Right? When you fold this side up, this would be the height of your box, but clearly this side is of length x. So your box is of height x. And now we're good to go, right? We want to maximize the volume of our box. So we have here a function of x only, call this f of x. You could also call it a of x for area, v of x for volume, doesn't matter. And again, the volume will be the area of the base, so 3 minus 2x times 3 minus 2x, so 3 minus 2x squared, times the height x. So the volume is quite simply x times 3 minus 2x squared. And now we're going to look at our interval of x values. And obviously f of x is continuous, as it is simply a polynomial, and it is a cubic polynomial. So what is the range for our x variable? Right? If you think of it, x is the amount of cardboard you cut off from each of the 4 corners. So you could say, I'll cut off 0. But clearly, if you cut off nothing from each corner, you're left with just a rectangular, a square base, and you have no flaps, no sides, and you'll get 0 volume. So we can include 0 in our interval, even though if x is 0, we have no box, the volume is 0, but that's why we can include 0, because clearly this will not give us a maximum value. When x is 0, the volume is 0. And I imagine, what's the largest possible value of x? Well, because you're cutting at both ends of a side an amount of x, the largest amount you can cut is when you meet the side midway. And so the length is 3, so the midpoint is 3 over 2. So x is at most 3 over 2. But once again, if you cut off a corner of each side, a square, from each corner with a length of 3 over 2, if you think of it, you're removing everything. So you're left with nothing, and you'll have 0 volume, which is again obvious from the function. If you plug in here x equals 3/2, 2 times 3/2 is 3, 3 minus 3 is 0. So again, we can include these two endpoints because we know that they will not yield a maximum value, because at both 0 and 3/2, the volume is 0. And now we're good to go. We have a continuous function on a closed and bounded interval. And so we know that the maximum value and minimum value of this function will occur at either the left-hand point, the right-hand point of the interval, or at some critical point inside of the interval. Well, to find the critical points, or point, we don't know, let's differentiate. So f prime of x. We have a product, so we use the product rule. Derivative of x is 1 times the second function, 3 minus 2x all squared, plus x, the first function, times the derivative of the second function. The outside function is the power 2. By the power rule, we get 2 times 3 minus 2x. 2 minus 1 is 1, but that's just the derivative of the power 2 times, by the chain rule, the derivative of the argument, and the derivative of 3 minus 2x is simply negative 2. As always, because we're looking for critical points, and again, the derivative is a polynomial, always defined, so the critical points will be values of x where the derivative is equal to 0. So we have to factor. Well, we have a common factor of 3 minus 2x. So 3 minus 2x. If we factor 3 minus 2x from this term, since we have 2, we're left with just the 1. And we factored it also from the second term, so it's gone. So what are we left with? A simple 3 minus 2x from the first term, plus x times 2 times negative 2 gives negative 4x. Three minus 2x times 3 minus 6x. We can factor 3 here, and we'll have, if you put it up front, 3 times 3 minus 2x. And you're left with 1 minus 2x. And now you have your derivative fully factored. And so this will be equal to 0 if and only if one of the factors is equal to 0. So if 3 minus 2x is 0, 3 equals 2x, therefore x is equal to 3/2. And we already had 3/2 as the right endpoint of our interval, nothing new here. But this term could be 0, and so if 1 minus 2x is 0, 1 equals 2x divided by 2, x is equal to 1/2, which is a second critical point which happens to be inside of the interval. Now that we have the two endpoints of our interval and the two critical points, we can look at a table of value. Our two endpoints, if I just look up, x equals 0. And as we have said before, f of 0 is simply 0. F of the right endpoint, 3 over 2. And as we have said before, when you cut off from each corner a square whose side is 3 over 2, you get nothing left, and so again, you get a volume of 0. 2 times 3/2 is 3. 3 minus 3 is 0. The volume is 0. And finally, 3/2 is already in our table. What if x is 1/2? Now, a critical point inside of our interval. Well, what is f of 1/2? Well, let's see. 1/2 times 2 is 1. 3 minus 1 is 2. 2 squared is 4. 4 times 1/2 is 2. And so the value for the volume is 2. And now we have a complete table, right? We have the value of the function at the endpoints of our interval and at the only critical point inside the interval. And so we know that from these three values, we have our minimum and our maximum value. Clearly, the minimum value is 0, and this is again obvious because we're looking here at the volume of our box. The smallest volume we can have is 0, and it's attained when we cut off nothing from the corner or a square whose side is 3 over 2. In each case, we get no box, so a volume of 0. But if we do cut off from each of the four corners a square whose length is a ½ meter, then we'll have our maximum value of the volume. So there you go. This is our conclusion. Clearly, 2 is the larger value between 0, 0. So, the maximum volume of our box is 2 meters cubed. And, well, how do we achieve this? By cutting from each of the four corners a square with sides equal to 1/2 meters, or if you prefer, 50 centimeters. And this is achieved by cutting a square whose sides are 50 centimeters from each of the four corners. Of our square piece of cardboard, right? So you will be able to construct the box with maximum possible volume if from the original square piece of cardboard, whose sides are of length 3 meters, you cut off 0.5 meters, so 50 centimeters, 50 centimeters, cut that same amount for each of the four corners. Once you fold those up, you'll have a box of maximum volume, and the maximum volume is 2 meters cubed. And that's it.